Assalamu alaikum. Today we'll be discussing Article 30.7 Displacement Current and the Journal form of Ampere's law. This will be the last article of chapter 30th that we'll be discussing, and then we'll move on to chapter number 31st. Okay, what is displacement current? It is when we have a situation in which we have something a closed loop and an open loop, and there we have already discussed about the Ampere's law, as that it includes the system which have closed loops in it. So when there came a problem when there is a closed loop connected with an open loop, the Ampere law fails to give the magnetic field in that particular scenario. So to approach that, Ampere and Faraday they conducted different experiment but failed to explain that. Then Maxwell gave a mathematical explanation for that, and after applying that mathematical explanation to the situation, they came to know that by introducing an additional term in the Ampere law, uh, they have the problem solved. So then the Ampere law was modified, and in the end of this article you'll see the new form of Maxwell Ampere's law. So now let us suppose that we have a capacitor, and the current this is the wire which is linked with the capacitor, and the capacitor is charging. Let us suppose that this is a circular plate, and the radius is r. Now with this current we get the changing electric field inside the capacitor, because we have a current in this wire, and the plates they start charging, and they keep on charging. As long as they keep on charging, the electric field inside the capacitor is changing. So mathematically, the electric field inside the capacitor is given as E is equals to sigma over kappa epsilon naught. Kappa is the dielectric constant, and from sigma we can write charge per unit area, that is Q over A kappa epsilon naught. And as this is a circular circular capacitor, so we can write the area to be Q over pi r square kappa epsilon naught. As the current is continuously running, the charges keep on building all the time, and so we can define current as a rate of change of rate of flow of charges. So dq by dt. So there will be changing E inside, which is dE by dt. So we can write this equation over here, and this equation. Okay, so by using this equation and differentiating it with respect to time, we get dE over dt equals to dq by dt multiplied by 1 over pi r square kappa epsilon naught, and this dq by dt gives me I, and I have this I over pi r square kappa epsilon naught. So this is equation number 1. You'll see that later on we'll be using this equation. Just keep this thing in mind. Only when the current is 0, then the electric field will be 0. So if there is no current through the wire, then there will be no electric field between the capacitor. So how does the magnetic field is affected? Let us suppose that we have these 2 points P1 and P2, and this is let us suppose that this is the point on a closed surface, and the radius of the closed surface is given by small r, whereas this capital R is the radius of the capacitor. So now if we want to find the magnetic field at point P, we see that this is a closed loop and the current is going through the closed loop, and if the current is going through the closed loop, then simply we will apply Ampere's law, that is closed integral B dot dl, which is equals to mu naught I. And by solving the entire closed loop, we'll get 2 pi r, and we can find the magnetic field. So skipping all the details over here, and now from here you can see that for that P1 we can easily apply Ampere's law, and we find mu naught I over 2 pi r. This is for P1. Now considering P2, so considering a closed loop there as I is 0, so the magnetic field at P2 is 0, which is absurd. There has to be a magnetic field. We cannot say that there is no magnetic field at point P2. So what is the mistake that we are doing over here? Uh, so let us suppose that we have something like a shopping bag, and you enclose that one plate of the capacitor in a shopping bag in such a way that the base of the bag is placed inside these two capacitor, and the open side is over here. So this is how you have placed this shopping bag uh, with the capacitor and the wire carrying current in it. So now we have to find again the magnetic field through this closed loop and this open area over here. So what we will do is for this P1, we'll see that again when we apply the Ampere's law, we will simply use that closed integral B dot dl equals to mu naught I, and by solving the closed integral we get B is equals to mu naught I over 2 pi r. But here as the current is penetrating this closed loop, but once it enters this open area over here, it is not penetrating the open area. So there the current in this case will be 0. So if the current is 0, then we'll get 0 magnetic field, which is actually not the case. So Maxwell suggested that there is something interesting happening between this uh, area over here, that is between the capacitors. So when this open area enters this area over here, that is between the capacitor, there we have a changing electric field, that is the flux is changing. And as the Faraday has suggested that changing magnetic flux can introduce a magnetic field, then why not changing a electric flux can produce a magnetic field? So he gave this theory, and then he formulated a formula, and after applying that formula to this open loop, you'll see that you get the same result as you did for the Ampere's law, and this is only being done by adding an additional term to the Ampere's law. So now what he suggested is like the electric flux is equals to, this is for the open surface, that is the open surface of the shopping bag, and it is E dot dA, both are vectors. So E dot dA is the flux. So Maxwell suggested that we add a term, that is rate of change of flux, to Ampere's law. So B dot dl is equals to mu naught I plus epsilon naught k d by dt integral E dot dA for the open surface. So this is an additional term that Maxwell added to Ampere's law. Now what this additional term will do, we'll see. The term that Maxwell added over here is famously known as the displacement current. Now applying Maxwell law to a flat surface, figure 1, and then to figure 2. For figure 1, we have already seen that we have a closed loop and the wire is penetrating through the loop, and we simply have this B equals to mu naught I over 2 by R. Now, from figure 2, you can see that we have this open area over here, and there the first term of this Ampere's law, this gets 0. So now we have an additional term over here, that is epsilon naught mu naught kappa and d phi e over dt. So now we have an additional term which we'll go through. So in this case the first term is 0, so I'm not going to write the first term in the Ampere's law. We have B dot 2 pi r equals to mu naught epsilon naught kappa d phi e over dt. We know that electric flux is EA, and here the area of the circular capacitor is pi r square, so I have written pi r square over here. And we have seen in equation 1 the value of dE over dt. So I'll replace the value of d over dt over here, and that is I over pi r square kappa epsilon naught, cancelling the terms which are common in the numerator and the denominators, and you'll see that we get this B equals to mu naught I over 2 pi r, which is exactly the same as we get for figure 1. So we can now say that magnetic fields are produced by conduction currents and the time varying electric field. So the problem which Ampere and Faraday failed to solve was solved by Maxwell by introducing an additional term known as the displacement current. Now we have an example 30.9. A sinusoidal varying voltage is applied across an 8 microfarad capacitor. The frequency of voltage is 3 kilohertz and voltage amplitude is 30 volts. Find the displacement current in the capacitor. So the given data is capacitance and the frequency, the voltage, we have to find ID. Angular frequency is given by 2 pi f, and by solving it we get the value 1.88 into 10 to the power 4 per seconds. Now we, from our previous knowledge, we know that delta V is equals to, if we have a sinusoidal wave, delta V maximum is equals into sine of omega t. We have the value of omega, putting in the value of omega, and also we know that Q is equals to C delta V, and we have to find displacement current. So for displacement current we have a rate of change of charge, and by putting in the value of small q over here and then replacing delta V from here, we differentiate it with respect to time, and we get the value 4.52 cos of 1.88 into 10 raised to the power 4 t. So here we see that the displacement current will vary with time in case of sinusoidal wave. So this is all about displacement current and chapter number 30th.